Hello everyone, welcome back to my channel. I am back with a video on determinants and inverses, and we're going to focus on 2 by 2 matrices. So matrices that have only 4 elements. So 1, 2, 3, 4 type matrices. So that's a 2 by 2 matrix. Okay, so let's understand what a determinant of a matrix is. So determinant of a 2 by 2 matrix. So in general, if you represent elements with letters A, B, C, D, we use the formula to find the determinant, so DET of whatever matrix. So let's say if you want to represent this matrix by the letter A, so we use DET of A. Sometimes we also use this to represent determinants. Okay, so determinants can be found by using the formula A times D minus B times C. So AD minus BC is the rule. So what is a determinant? So a determinant is a number. This number is just a scaling factor, basically. It's a scaling factor, represents a linear transformation, scaling factor of a linear transformation. The determinant can be positive or negative or 0 as well. So this number tells us how a matrix expands or contracts in space. Let's take an example to find the determinant of a matrix. Let's say I call it matrix A. Let the elements be 4, 3, 8, and 2. And I'm going to use that formula AD minus BC. So A is 4, B is 8, C is 3, and D is 2. So the determinant of A is going to be 4 times 2 minus 3 times 8. So that's 4 times 2 is 8 minus 24. So negative 16, and it's okay to have a negative determinant. So it's just that the orientation of this matrix would flip because of the negative. Okay, another concept I would like to discuss is the concept of a matrix being singular or non-singular. So if the determinant of a matrix equals to 0, so if the determinant is 0, then the matrix is called a singular matrix. Okay, so, or there's another word, non-invertible matrix. For such matrices, there do not exist any inverse, no inverse of such a matrix. Okay, so let's take an example. Let me call some matrix B. So 5, negative 1, 10, and negative 2. So let's find the determinant of this matrix. So 5 times negative 2 minus negative 1 times 10. So negative 10 plus 10 is 0. So this matrix is what we call is a singular matrix. Okay, this is non-invertible. It does not have an inverse. Okay, so therefore, what is the inverse of a matrix? Okay, so inverse of a 2 by 2 matrix. So inverse is written by some matrix to the power of negative 1. So if A is the matrix to the power of minus 1 is the inverse. Now this is not the same as 1 over A. Okay, so to find the inverse of a matrix, we need two things. We need the determinant, and we also need something called the adjugate. Now, what is this adjugate? Okay, so coming back to our general matrix A, B, C, D, if you were to find the adjugate of this matrix, what you would do is you are going to swap the A and D. So D comes here and A goes there, and change the signs of whatever the B is and C is. So if this B originally had a minus sign, it becomes a plus sign. Okay, so that's what it means, reverse the sign of the B and C. Okay, let's take an example. Let us take a matrix C. Okay, 1, 2, -3, and 4 is the matrix. Let's find the determinant first. Determinant of C is going to be 1 times 4 minus 2 times -3. So that's 4 minus 6, which is a 10. So 10 is the determinant. Now we need to find the adjugate. So the adjugate of C, so swap the A and D. 4 comes here, 1 goes there. So 3 has a negative sign, so its sign gets reversed. Okay, so that becomes +3. 2 is already positive, make it negative. Oops, that does not look like a minus. Okay, now so the inverse of any matrix is written by 1 over the determinant of the matrix. Let me make that a C. Let me change that to a C. So that's determinant 1 over, it's always 1 over the determinant of C times the adjugate of C. So the matrix should be, guys, so C inverse, the inverse of this matrix, C inverse would be 1 over the determinant, so 1 over 10, and the adjugate 4 minus 2, 3, 1. Okay, and then if I multiply, or rather divide every element by 10, 4 tenths becomes 2 fifths, that becomes -1/5, 3 tenths, and 1 tenth. So that's the inverse of this matrix C. Now I'm going to talk about something called the identity element, or identity matrix, sorry, identity matrix. So it's a special matrix. For a 2 by 2 matrix, the identity matrix looks like 1, 0, 0, 1, where the diagonal elements are 1. For a 3 by 3 matrix, the identity matrix looks like 1, 0, 0, 0, 1, 0, 0, 0, 1. So the diagonal elements are all 1, everything else is 0. Okay. A property in relation to the identity matrix is that every time you multiply a matrix A by the identity matrix, or the identity matrix by A, you get the matrix itself. So therefore, if you multiply a matrix by its inverse, you should always get the identity matrix. So in the case of our example, if you were to multiply the matrix C, so the matrix C was 1, 2, minus 3. In fact, let me just use a fresh page. Okay, so let's take the matrix C, 1, 2, minus 3, 4, and multiply by the inverse, 2 fifths, -1/5, 3 tenths, and 1 tenth. Okay, so if you guys remember from our previous video how we did matrix multiplication, I'm going to follow that. So 1 times 2 fifths plus -3 times -1/5. Okay, next 1 times 3 tenths plus -3 times 1 tenth. Next element, 2 times 2 fifths plus 4 times -1/5. And the last element, 2 times 3 tenths plus 4 times 1 tenth. Okay, so let's evaluate this. So that becomes 2 fifths. Minus and minus is plus, so plus 3 fifths. Next, 3 tenths minus 3 tenths. Next, 4 fifths minus 4/5 and 6/10 plus 4/10. Okay, and finally that's a 5/5. That becomes a 0, that's a 0, and that's 10/10, which means this gives us 1, 0, 0, 1. And this confirms that when you multiply the matrix C by its inverse, you get the identity matrix. Okay, that's it, guys. I hope you learned something about determinants and inverses of a 2x2 matrix. In my next video, I might look at solving matrix equations. And thank you very much for watching. Have a nice day. Bye-bye.